Good morning, everyone. We are from Group 3. Our title is 3.1 Newton's Universal Law of Gravitation. Gravitational force, universal force, acts between any two bodies in the universe. Two relationships that involve gravitational force between two bodies. Gravitational force is directly proportional to the product of the masses of the two bodies. That is, F equal to m1, m2. Gravitational force is inversely proportional to the square of the distance between the center of the two bodies. That is, F equal to 1 over r squared. Formulation of Newton's universal law of gravitation. F equal to m1 and 2 over r squared. F equal to g m1 and 2 over r squared. F is equal to gravitational force between two bodies. M1 is equal to mass of the first body. M2 is equal to mass of second body. R is distance between the center of the first body and the center of the second body. G is equal to gravitational constant. G is equal to 6.67 multiplied 10 power negative 11 and m squared kg power negative 2. Effect of mass and distance between two bodies on gravitational force. F1 less than F2, the larger the mass of the body, the larger the gravitational force. F1 greater than F2, gravitational force decreases when the distance between the two bodies increases.
Relating gravitational acceleration on the surface of the Earth with universal gravitational constant. According to Newton's second law of motion, gravitational force can be expressed as F equal to mg from Newton's universal law of gravitation. Gravitational force is expressed as F equal to g m1 m2 over r squared. The diagram below shows a spread of a graph with various values of gravitational acceleration g and distance r from the center of the Earth. From the graph, we know that value g is directly proportional to the distance from the center of the Earth, and value g is inversely proportional to the square of the distance from center of the Earth. The figure below shows a satellite at a height h from the surface of the Earth. R is the radius of the Earth, and R is the distance of the satellite from the center of the Earth, which is the radius of the orbit. At height h from the surface of the Earth, distance from the center of the Earth is R equal to R plus h. With this, the gravitational acceleration g is equal to gm over r plus h squared. On the surface of the Earth, height h is equal to 0. Therefore, r is equal to radius of the Earth, r. Gravitational acceleration on the surface of the Earth, g is equal to gm over r squared, where m is the mass of the Earth. Next, we look for example 1. Mass of the Earth is 5.97 times 1024 kg and radius of the Earth is 6.37 times 10 power 6 meter. Calculate gravitational acceleration on the surface of the Earth. Given that g is equal to 6.67 times 10 power negative 11 Newton meter square kg power negative 2. First, we need to list down the information with symbol. M is equal to 5.797 times 1024 kg. G is equal to 6.67 times 10 power negative 11 Newton meter square kg power negative 2. And last, the R is equal to 6.7 37 times 10 power of 6 meter. Next, we write down the formula we need to use. That is the G equal to Gm over R squared. Last, we substitute the numerical into the formula and perform the calculation. G is equal to 6.67 times 10 negative 11 times 5.97 times 10 24 over 6.37 times 10 power of 6 squared. The answer of the gravitational acceleration on the surface of the Earth is equal to 9.81 ms negative 2. Next, we look at example 2. A Kada imaging satellite orbit around the Earth at a height of 418 km. What is the value of gravitational acceleration at the position of the satellite? Given that G is equal to 6.67 times 10 power negative 11 Newton meter square kg power negative 2. M is equal to 5.797 times 10 power of 24 kg and R is equal to 6.37 times 10 power of 6 meter. First, we need to convert the height of the orbit h 418 km into meter. Next, we choose the formula we need to use and substitute the numbers into the formula. Last week, get the answer is equal to 8.59 ms negative 2.
Centripetal force in the motion of satellites and planets. Figure 3.13 shows three positions of a satellite which orbits around the Earth at a uniform speed. An object in circular motion always experiences changes in the direction of its motion even though its speed is fixed. Force is required to change the direction of motion of a body. Smart before. When a body moves in a circle at a uniform speed, the body is said to be in uniform circular motion. Centripetal force in the motion of satellites and planets. Centripetal force is a force S on the body in a direction towards the center of the circle. Figure 3.16 shows the tension in the rope that acts as the centripetal force for the motion of the rubber stopper. The magnitude of the centripetal force depends on the mass of the body, the linear speed, and the radius of the circle. Centripetal force can be calculated by using the formula. F equals mv squared over r, where F is equal to centripetal force, m equal to mass, v equal to linear speed, r equal to radius of circle. Smart info. When a body is rotated at a certain uniform speed with the string almost horizontal, the effect of gravitational force on the circular motion of the body can be ignored. Though the speed is uniform, the direction of motion of the body keeps changing. Smart info. Linear speed shows how fast a body moves in a circular motion. Example 1. Figure 3.17 shows a hammer throw a lead swinging an iron ball in a horizontal circle before releasing it. What is the centripetal force that acts on the iron ball when the iron ball is moving at a speed of 20 meters per second? M equal to 7.2 kg, V equal to 20 meters per second, and R equal to 1.8 meter. Then we use the formula F equal mv squared over R. Thus, the centripetal force is 1,600 Newton. Can a satellite orbit the Earth without being driven by a rocket engine? The possibility of such movement was predicted by Isaac Newton in the 17th century as shown in figure 3.18. Object launches with low linear speed will follow trajectory 1 and reaches the Earth at Q. Object launches with sufficiently high linear speed will follow trajectory 2 circulating the Earth. The object will not return to the Earth.
The prediction of Newton is now a reality with so many man-made satellites orbiting around the Earth without being driven by any thrust. Satellites always experience gravitational force acting towards the center of the Earth. The gravitational force on satellites acts as centripetal force. By comparing the formula for force, F equal to ma, and formula for centripetal force, F equal to mv squared over r, we obtain centripetal acceleration, A equal to v squared over r, where v equal to linear speed of satellite, r equal to radius of the orbit of satellite. Example 1. Figure 3.19 shows a weather satellite orbiting the Earth at a height h equal to 480 km. Linear speed of the satellite is 7.62 multiplied 10 power 3 ms negative 1. The radius of the Earth r is r equal to 6.37 multiplied 10 power 6 meter. What is the centripetal acceleration of the satellite? Solution. Step 1. List the given information in symbols. Height of satellite is equal to 480,000 meter. Linear speed of satellite v equal to 7.62 multiplied 10 power 3 ms negative 1. Radius of the Earth r equal to 6.37 multiplied 10 power 6 meter. Identify and write down the formula used. A equal to v squared over r. Step 3. Substitute numerical values into the formula and perform the calculations. A equal to v squared over r plus h. Then the centripetal acceleration of the satellite is 8.48 ms negative 2. Mass of the Earth and the Sun. Formula for the mass of the Earth and the Sun can be derived by using the formula of Newton's universal law of gravitation and the formula for centripetal force. Force formula used to determine the mass of the Earth or the Sun is m equal to 4 pi squared r cubed over gt squared. Data needed to calculate the mass of the Earth is radius of the orbit of any satellite or the moon and the period of revolution. Data needed to calculate the mass of the Sun are radius of the orbit of any planet and the period of revolution of planet concerned. Thanks for listening.